Hello students, welcome to AskPrep. My name is Gaganapi. In today's class, we will study the continuation of chemical bonding chapter. The next concept here is dipole moment. So what is basically dipole moment? So it is defined as the product of magnitude of the charge and the distance between the centers of positive and negative charge. And it is designated by the Greek letter mu. And mathematically it is expressed as dipole moment is equals to charge multiplied by distance of separation. And this dipole moment is usually expressed in dB units. And the conversion factor is 1 dB is equals to 3.33564 into 10 power minus 30 coulomb. So the dipole moment of HF is represented as given below. So HF, this is dipole moment. It is given as mu. And this arrow, it symbolizes the direction of the shift of electron density in the molecule. So in polyatomic molecules, the dipole moment, it do not depend only upon the individual dipole moments of bonds is known as bond dipole. So, but it also depends on the spatial arrangement of various bonds in the molecule. For example, in H2O molecule, it has bent structure and the two OH bonds are oriented at an angle of 104.5 degree. And the resultant dipole moment of the two OH bonds are C. So let us study an interesting case of NH3 and NF3 molecule. These both molecules have a pyramidal shape with a lone pair of electrons on the nitrogen atom. So although the fluorine is the most electronegative atom than the nitrogen, the dipole moment of NH3 is greater than that of NF3. Why? Because in NH3, the orbital dipole due to the lone pair is in the same direction in NH bonds, whereas in NF3, the orbital dipole is in the opposite direction. Effect of the resultant NF bond moments. As a result, lower the dipole moment of NF3. So Fajans rule. So in Fajans rule, what happens here is he basically gave an explanation about the covalent and the ionic bonds. The smaller the size of the cation, the larger the size of the anion. That is the reverse case. And the covalent character is more. So if the charge on the cation is more, the covalent character of the ionic bond is also more. For cations of the same size and the charge, the electronic configuration, that is N-1 Dn Ns0, and that of transition metals is more polarizing than that of the noble gas configuration, that is Ns2 Np6, which is typical of alkali and alkaline earth metal cation. And the cation polarizes the anion, which helps in pulling the electron charge towards itself and therefore increasing the charge between the two atoms. And this is what exactly happens in a covalent bond, where electron density is built up in between these two nuclei. And the polarizing power of the cation and the polarizability of the anion and the extent of the distortion of anion are the main factors which determine the percentage of the covalent character of the ionic bond. So the next is valential electron pair repulsion theory. So Sidbeck and Powell in 1940, they proposed a simple theory which is based on the repulsive interactions of the electron pairs in the valential of the atom. So what are the main postulates of the VSEPR theory? So the shape of a molecule depends upon the number of valential electron pairs around the central atom, and the pairs of the electrons in the valence shell they repel one another as their electron clouds are negatively charged. And these pairs of electron, they tend to occupy positions in a space which minimize repulsion and they maximize the distance between each other. And the valence shell is taken as a sphere with the electron pairs surrounding and at a maximum distance separating from one another. And a multiple bond is treated as if it is a single electron pair, and 2 or 3 electron pairs of a multiple bond are treated as a single superpair. So one or more two resonance is applicable to such kind of structures. So the repulsive interaction of electron pair decreases in the bond order. So lone pair greater than lone pair, bond pair greater than bond pair, bond pair. So with the help of the VSEPR theory, we can divide molecules into two categories as molecules in which central atom has no lone pair, or else molecules in which central atom has one or more lone pairs. And the VSEPR theory is able to predict geometry of a large number of molecules, especially the compounds of p-block elements, very accurately. And it also helps in determining the geometry with the help of the energy difference is very small in the structures. And this theoretical basis of the VSEPR theory regarding the effects of electron pair repulsion on molecular shapes is very good, and it is a subject of discussion. See, number of electron pairs is 2. So there are arrangement of electron pairs around the central atom is 2. We can see BAB in the sense 2 other bonded atoms and 1 the central atom, that is A, which is linear with an angle of 180 degree. And the examples of such kind of molecules are BeCl2, HgCl2 and BeBr2. If the number of electron pairs are 3, then it is trigonal planar with an angle of 120 degree. Examples are BF3, BCl3 and BH3. These are 5. The shape is the trigonal bipyramidal with the example of BCl5, SPF5 and ASF5. So this is how the central atom here is phosphorus and all the chlorine atoms are surrounded in this way. If the number of electron pairs are 6, then it is octahedral. So it is SF6, TF6 and so on. So this is the shape of some molecules having one or more lone pairs of electrons. So if the molecule is AB2E type, the number of bonding pairs are 2 and the number of lone pairs are 1. So E is taken as the lone pair here. So the arrangement of electron pairs is trigonal planar and the shape is bent. And example is SO2 and O3. So if the molecule is AB3E type, number of bonding pairs is 3, number of lone pairs is 1. So it is tetrahedral arrangement of electron pair and the shape is trigonal pyramidal. The example NH3. So if the molecule type is AB3E2, so the number of bonding pairs are 2 and number of lone, it is AB2, so the number of lone pairs are 2 and it is tetrahedral bent H2. So the next is AB4E. So the number of bonding pairs are 4, number of lone pairs is 1. So it is trigonal bipyramidal with C-shape and example is SF4. The next is AB3E2. E2. So the number of bonding pairs is 3, number of lone pairs is 2, but trigonal, bipyramidal and T-shape. It is ClF3. The next one is AB3 or AB5E. So the number of bonding pairs are 5, lone pair is 1, so it is octahedral. Shape is square pyramid. Example is BRF5. So the next is AB4E2. So the number of bonding pairs is 4, number of lone pairs is 2, octahedral, square, planar with the example XCF4. So this is the molecule type, and the reason why it is given as the shape is explained here. For AB2E molecule, it is a bent shape. So this is because of the lone pair of electron which undergoes repulsion is more compared to the bonded pair electron. So the bond angle is reduced from 119.5 degree to 120 degree. Here AB3E is trigonal pyramidal. So this is in the case of NH3 molecule, where this is also due to the lone pair bond pair repulsion, which is more than the bond pair repulsion, and the angle is reduced from 107 to 109.5. So the next is AB2E2. So it is bent shape. So if the bent shape is due to the lone pair repulsion is more than the bond pair repulsion. So the angle is reduced to 104.5 degree from 109.5 degree. So the next is AB4E. So the number of bonding pairs is 4 and the number of lone pairs is 1. Here it is seesaw shape. A lone pair is present at the axial position. So there are 3 lone pair bond pair repulsions at 90 degree. In the lone pair is in equatorial position and there are 2 lone pair bond pair repulsions. Hence arrangement is more stable. Here AB3E2 is a T shape. Lone pairs are present at the equatorial position. So there is a less lone pair bond pair repulsion as compared to others. So from VSEPR theory, we came to a conclusion of studying the geometry of simple molecules, but theoretically it couldn't explain properly and there are certain limitations, and as a result 2 other new theories were developed, that is VBT and MOT, valence bond theory and molecular orbital theory. So then what are the basic assumptions of the valence bond theory? Atom can share its electron with other atoms to form bonds which results in the formation of molecule. And the atoms do not lose their identity even after the formation of molecule. And only the valence electrons are involved in bond formation and the inner electrons do not participate in the bond. During the bond, only the valence electrons of the bonded atom, they lose their identity, whereas the inner electrons are not affected. And the stability of the bond is given in terms of energy release during the bond formation. So if more the energy release, stronger the bond. So considering 2 hydrogen atoms of A and B approaching each other, they have nuclei Na and Nb and electron present in them are represented as A and B. When 2 atoms are present at large distance from each other, so there is no interaction between them. So as a result, 2 atoms approach each other and the attractive and the repulsive forces begin to operate. So attractive force arise between the nucleus of one atom and its own electron, that is Na Ea and Nbe, nucleus of one atom and electron of another atom, Na-Eb and Nb-Ea. Similarly, the repulsive forces also Ea-Eb and Na-Nb is the same. The magnitude of the attractive force is more than that of the repulsive force. So as a result, what happens? Two atoms, they come closer. As a result, they attract each other and the potential energy gradually decreases. And at a state where a net force of the attraction balances the force of repulsion and attraction, and the system, it acquires the minimum energy. And two hydrogen atoms are said to be bonded together and it forms a stable molecule having a bond length of 74 picometer. As the energy gets released when the bond is formed between two hydrogen atoms, the hydrogen molecule is more stable than that of isolated hydrogen atoms. So the energy released is called as bond enthalpy. So the amount of energy which is required to dissociate 1 mole of H2 molecule is 434.8 kilojoule. So this is how the attractive and the repulsive forces act upon the H2 molecule. So we have seen HA, HB, EA, EB. So HA and EB lies on one side, HB and EA lies on one side. So it is the same, the attractive force and the repulsive force. And this is the potential energy curve which helps in the formation of H2 molecule as a function of internuclear distance of the hydrogen atom. So the next is orbital overlap. During the formation of hydrogen molecule, there is a minimum energy state where two hydrogen atoms are very near so that their atomic orbitals undergo partial interpenetration. So this partial merging of atomic orbitals is called overlapping of atomic orbitals, which results in the pairing of electrons. And the extent of overlap which determines the strength of the covalent bond. So in general, what happens? Greater the overlap, stronger the bond formed between the two atoms. So according to the orbital overlap concept, what happens? The formation of a covalent bond between two atoms results by pairing of electrons which is present in the valence shell having the opposite spins. So the next is directional properties of bonds. So this valence bond theory, what happens? It explains the shape, the formation, the directional properties of bonds in polyatomic molecules like CH4, NH3 and H2O in terms of overlap and hybridization of atomic orbitals. So in case of the shape and the formation, geometry is also very important for the bond formation. So the next concept is overlapping of atomic orbitals. So what happens when orbitals of two atoms come very close to each other to form a bond? Their overlap may be positive, negative or zero depending upon the sign and the direction of orientation of amplitude on the wave function. So if the orbital has same sign and orientation in space, then it is called a positive overlap. So if it has a different sign and orientation, then it is a negative overlap. So for a simple molecule like CH4 and all, the bond angle varies with the original calculation. In case of NH3 and H2O, so HNH and HOH molecule angles should be 90 degree, but actually it is 107 and 104.5 in NH3 and H2O molecules. So that is why studying these properties of the molecules with respect to the overlapping is also important. So this is the positive overlap with the same sign and same phase of orientation. Negative overlap, and this is the zero overlap. In the case of positive overlap, this is zero overlap. In case of negative, this is the p orbital, s orbital, p orbital, s orbital. Overlapping takes place. The sidewise overlapping of p orbital. So the next is types of overlapping and the nature of covalent bonds. So the covalent bonds are classified into two types based upon the overlapping: sigma bond and pi bond. Sigma bond is this type of covalent bond is formed by the end-to-end overlap of bonding orbitals along with the internuclear axis, and this is called as head-on overlap or egg-gel overlap. So this is formed by the two types of formation of atomic orbitals. So one is SS overlapping. So in this case what happens? There is overlap of two half-filled s orbitals along with the internuclear axis as shown. So s orbital with the help of the internuclear axis, overlapping takes place. So the next is sp overlapping. This occurs between half-filled s orbitals of one atom, half-filled p orbitals of one atom. So between these two internuclear distances, overlapping takes place. So the next is pp overlapping. So it is between the half-filled p orbitals of the two atoms. So the next is pi bond. So what happens in pi bond? In formation of pi bond, the atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis. And these are also formed due to sidewise overlapping, consist of two charged clouds above and below the plane of the atoms. So the next is strength of sigma and pi bonds. So basically the strength of a bond depends upon the extent of overlapping. So in case of sigma bond, the overlapping of orbitals take place to a larger extent. So hence it is stronger as compared to the pi bond, where the extent of overlapping occurs to a smaller extent. So further, it is important to note that in the formation of a multiple bond between the two atoms, that is pi bond is formed in addition to a sigma bond. So the next concept is hybridization. So this concept was introduced by Pauling. Here atomic orbitals combine to form new set of equivalent orbitals, which is known as hybrid orbitals. And hybridization is defined as the process of intermixing of orbitals of slightly different energies. As a result, it helps in formation of new set of orbitals of equivalent energies and shape. So the salient features of hybridization: the number of hybrid orbitals formed is equal to the number of atomic orbitals which gets hybridized, and the hybrid orbitals are always equivalent in energy and shape. And the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. And these hybrid orbitals are directed in some preferred directions to have minimum repulsion between the electrons, which results as a stable arrangement. So the type of hybridization indicates the bond formation in the molecules. So the basic conditions of hybridization: the orbitals present in the valence shell of an atom are hybridized, and the orbitals which undergo hybridization has equal energy, and the promotion of electron is not an essential condition prior to hybridization, and it is not necessary that only half-filled orbitals participate in the hybridization. In some cases, even fully filled orbitals also takes place in the hybridization. So types of hybridization, which is based on the sp d and f orbitals. Sp hybridization. So this is involving mixing of 1s and p orbital, resulting in form two equivalent sp hybrid orbitals. So the orbitals which is suitable for this hybridization is s and pz orbitals, as the hybrid orbitals should lie in the z-axis. So each sp hybrid orbitals has 50% s character and 50% p character. So such a molecule in which the central atom is sp hybridized and it is linked directly to other central atoms which possess linear geometry. So this type of hybridization is known as the diagonal hybridization. So example is BeCl2. So BeCl2, it is the angle of 180 degree and 1s and 2p orbitals of chlorine, it axially overlap to form BeCl sigma bonds. So this sp hybridization, it takes place in C2H2 molecule also with the help of 2py and 2px hybrid orbitals. So one sp hybrid orbital of one carbon atom, it overlaps axially with sp hybrid orbital of other carbon atom to form carbon-carbon sigma bond, while the other hybrid orbitals of each carbon atom overlap axially with half-filled s orbitals of hydrogen atoms, forming sigma bond. So what happens to unhybridized p orbitals of both the carbon atoms? They overlap sideways to form two pi bonds between the carbon atoms. So the triple bond between the two carbon atoms is made up of 1 sigma and 2 pi bonds. sp2 hybridization. So this hybridization, there is involvement of 1s and 2p orbitals in order to form 3 equivalent sp2 hybridized orbitals. So for example, in BeCl3 molecule, the ground state electronic configuration of boron atom is 1s2, 2s2, 2p1. So in the excited state, 2s electron is promoted to vacant 2p orbital. As a result, boron has 3 unpaired electrons. So these 3 orbitals, 1s and 2p, they hybridize to form 3 sp2 hybrid orbitals. And the 3 hybrid orbitals which are formed are oriented in a trigonal planar arrangement which overlap with the 2p orbitals of chlorine to form 3 BCl bonds. So in BCl3, the geometry is trigonal planar with fluorine, boron fluorine bond angle of 120 degree. So in the formation of ethene molecule, one of the sp2 hybrid orbitals of carbon atom, they overlap axially with sp2 hybrid orbital of another carbon atom to form carbon-carbon sigma bond, while the other two sp2 orbitals of each carbon atom, they are used in making sp2s sigma bond with the two hydrogen atoms. So in ethene molecule, the carbon-carbon bond consists of one sp2 sigma bond and one pi bond between the p orbitals, and these are not used in the hybridization as they are perpendicular with the plane of the molecule with the bond length of 134 picometer, and the CH bond is sp2s sigma bond with bond length of 108 picometer, and the HCH bond angle is 117.6, which is, while the HCC bond angle is 121 degree. So sp3 hybridization. So this type of hybridization, which is explained by taking an example of CH4 molecule, in which there is mixing of 1s orbital and 3p orbitals of the valence shell to form 4 sp3 hybrid orbitals of equivalent energies and shape. So there is 25% s character and 75% p character in each sp3 hybrid orbitals. And the 4 sp3 hybrid orbitals which are formed are directed towards the 4 corners of the tetrahedron, and the angle between the sp3 hybrid orbital is 109.5 degree, which is in the case of CH4 molecule. And the structure of NH3 molecule is also explained with the help of sp3 hybridization. So in NH3, the valence shell electronic configuration of nitrogen in the ground state is 2s2, 2px1, 2py1, 2pz1, which have 3 unpaired electrons in the sp3 hybrid orbitals and lone pair of electrons which is present in the fourth one. And these 3 hybrid orbitals overlap with 1s orbitals of hydrogen atom to form 3 NH sigma bonds. So we know that force of repulsion between a lone pair and a bond pair is more than the force of repulsion between 2 bond pairs of electron. So as a result, the molecule gets distorted and the bond angle is reduced to 107 from 109 degree, and the geometry will be pyramidal. So in case of H2O molecule, 4 oxygen atoms orbitals undergo sp3 hybridization, forming 4 sp3 hybrid orbitals, so out of which contains 1 electron each and the other 2 contains a pair of electrons. So these 4 sp3 hybrid orbitals, it acquire a tetrahedral geometry with 2 corners occupied by hydrogen atoms while the other 2 occupied by the lone pairs. And the bond angle is reduced to 104.5 to 109, and the molecule acquires a B shape or a angular geometry. So sp3 hybridization in C2H6 molecule. So in ethane molecule, both the carbon atoms assume have sp3 hybridized state. So out of that, 4 sp3 hybrid orbitals of carbon atom overlaps axially with similar orbitals of other atom to form sp3 sigma bond, while the other 3 hybrid orbitals of each atom are used in forming sp3s sigma bonds, while the hydrogen atoms also occupied. Therefore, this carbon-carbon bond length is 154 picometer and each carbon-hydrogen bond length is 109 picometer. So hybridization of elements involving d orbitals. So in d orbitals, what happens? S, P and D, all these 3 orbitals combine together. So energy of the 3D orbital is more than that of 3s and 3p. So and the energy of the 3D orbitals are also more than 4s and 4p. So as a result, hybridization involves 3s 3p or 3d or 3d or 4s and 4p is possible. So the difference of energies in 3p and 4s is significant. No hybridization involving 3p, 3d and 4s orbitals is possible. So square planar, the hybridization is dsp2. The atomic orbitals combined are ds and p2. Examples are NiCN4 2- and PtCl4 2-. So the next is trigonal bipyramidal. The hybridization is sp3d, s plus p3 plus d. Examples are pf5 and pcl5. And square pyramidal shape sp3d2 and the atomic orbitals are s, p3, d2 and the examples are bf5. Octahedral sp3 d2 or d2 sp3. So 1s 3p d2 orbitals and the examples are sf6, crf6 3-, CONH3 6 Formation of PCl5, that is sp3d hybridization molecule. So the ground state and the excited state outer electronic configuration of phosphorus is represented as below, that is ground state is 1s2, 2s2, 2p6, 3s2 and 3p3, whereas in excited state it is 1s2, 2s2, 2p6 and 3s1. There are 5 different orbitals, 1s, 3p and 1d, which is available for hybridization. As a result, set of 5 sp3d hybrid orbitals which are directed towards the 5 corners of the trigonal bipyramidal. So in PCl5, the 5 sp3d orbitals of phosphorus overlap with the singly occupied p orbitals of chlorine atoms, and it form PCl sigma bonds, and 3 PCl bond lie in one plane and which make an angle of 120 degree with each other, and these bonds are termed as equatorial bonds, and the remaining 2 PCl bonds which is lying one above and one below the equatorial plane which make an angle of 90 degree with the plane. So these bonds are called axial bonds. So as the axial bonds which suffer more repulsive interaction from the equatorial bonds, and they have a slightly longer and slightly weaker than the equatorial bonds, which make PCl5 more reactive. Formation of SF6, that is sp3d2 hybridization. Here it is the electronic configuration is 3s2 and 3p4, and the excited state 1s, 3p and 2d orbitals are occupied, and these orbitals they hybridize to form 6 new sp3d2 hybrid orbitals, and which are projected towards the 6 corners of a regular octahedron is SF6. So these 6 sp3d hybrid orbitals they overlap with singly occupied orbitals of fluorine atoms and form 6 SF sigma bonds. So the next concept is molecular orbital theory, and this theory was developed by Pfund and Mulliken in 1932. So the salient features of this theory are: the electrons in the molecule are present in various molecular orbitals, as the electrons of atoms are present in the various atomic orbitals, and the orbitals of comparable energies and proper symmetry combine to form molecular orbitals. While an electron in an atomic orbital is influenced by one nucleus in a molecular orbital, it is influenced by 2 or more nuclei depending upon the number of atoms in a molecule. Therefore, an atomic orbital is monocentric while a molecular orbital is polycentric. The number of molecular orbital which is formed is equal to the combining atomic orbitals. So when 2 atomic orbitals combine, 2 molecular orbitals are formed. So one is known as bonding molecular orbital, while the other is called antibonding molecular orbital. So the bonding molecular orbital has lower energy and it has greater stability than the corresponding antibonding molecular orbital. So as the electron probability distribution around the nucleus in an atom is given by an atomic orbital, so the electron probability distribution around group of nuclei in a molecule is given by a molecular orbital. So the molecular orbital, according to the Alpha principle, it obeys the Pauli's exclusion principle and the Valence rule. So formation of molecular orbitals or the linear combination of atomic orbitals. So considering an hydrogen atom with the hydrogen molecule with 2 atoms A and B. So in ground state it occupies 1 electron in 1s orbital, and the atomic orbitals is represented by the wave function psi A and psi B. So mathematically it is represented by the linear combination of atomic orbitals, which is occurring by the addition and subtraction of the wave functions of individual atomic orbitals, that is psi MO is equals to psi A plus psi B. So therefore the 2 molecular orbitals sigma and sigma star are formed as sigma is psi a plus psi b, and sigma star is the opposite, psi a minus psi b. So the molecular orbital sigma, which is formed by the atomic orbital, so if it is formed by the addition, it is called bonding molecular orbital, while if it is formed by the subtraction, it is called anti-bonding molecular orbital. So this is the difference between bonding and anti-bonding molecular orbital. So bonding molecular orbital formed by addition, anti-bonding formed by subtraction of overlap of atomic orbitals. And the wave function is psi mo is equals to psi a plus psi b, psi star mo is equals to psi a minus psi b, and the formation takes place if the orbitals have same signs. So if the formation takes place when the lobes of the orbitals have different signs, and the energy of bonding molecular orbital is lower than that of atomic orbitals from which it is formed, and the energy of anti-bonding molecular orbital is higher than that of atomic orbitals from which it is formed, and the electron density is high in the case of the region between the nuclei of bonded atoms, and the electron density is low here, and every electron in bonding molecular orbitals contributes towards the attractive force, and every electron in anti-bonding contributes towards the repulsive force. So conditions for the combination of atomic orbitals. The combining atomic orbitals have same or nearly the same energy. So it indicates that 1s orbitals combine with the other 1s orbital but not with the 2s orbital, because the energy of 2s orbital is higher than that of 1s orbital. So this is not true in all case of atoms, and the combining atomic orbitals have the same symmetry about the molecular axis. So if the z axis is combined with the z axis of the other atom, that is 2pz, 2pz, but not with 2px or 2py, because they are different symmetries. And the combining atomic orbitals must have this maximum to the extent. So greater the overlap, greater will the electron density between the nuclei of a molecular orbital. So the next is types of molecular orbitals. So molecular orbitals of diatomic molecules are designated as sigma, pi and delta. So the sigma molecular orbitals are symmetrical around the bond axis, while pi molecular are not symmetrical. So the combination of 1s orbitals towards the nucleus is sigma 1s and sigma star 1s, whereas in if the internucleus is taken in the z direction or the z axis, the combination of 2pz is sigma 2pz and sigma 2p star z. So this is producing 2 sigma molecular orbitals. So from 2px and 2py, they are not symmetrical because of the presence of positive and the negative lobes on the molecular plane. So they are labeled as pi and pi star. So if it is symmetrical, it is sigma. If it is non-symmetrical, it is pi. So sigma bonding has a higher electron density and the internuclear distance, whereas the pi star has a node between the nuclei. So the next is energy level diagram. So this is how an atomic orbitals are represented as sigma 1s and sigma star 1s. So in the same way, in 2s and 2p orbitals also, they give rise to 8 molecular orbitals. So anti-bonding molecular orbitals, so sigma star 2s, sigma star 2pz, pi star 2px and pi star 2py, and bonding molecular orbital sigma 2s, sigma 2pz and pi 2px and pi 2py. So this is the increasing order: sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma star 2, sigma 2pz, pi 2px, pi 2py, and lesser than pi star, and at end it is sigma star 2pz. So here this energy is same for lithium molecule, beryllium, boron, carbon, nitrogen, such as, and it is experimentally found to be true for boron, carbon and nitrogen. and the increasing order of energies of various molecular orbital is given below here, and the energy of the 2p molecular orbital is higher than that of pi 2p x and pi 2p y molecular orbital. So the energies of always sigma is higher than that of pi. So this is for sigma bond, sigma bonding, pi anti bonding, sigma anti bonding. So electronic configuration and their molecular behavior. So the distribution of electrons around the various molecular orbitals is called the electronic configuration. So stability of the molecules based upon the number of electrons occupying Nb is the bonding orbitals, Na is the anti-bonding orbitals. So if the molecule is stable, Nb is greater than Na, so more bonding orbitals are occupied, so the bonding influence is stronger and a stable molecule occurs. So if the molecule is unstable, Nb is less than Na, so the anti-bonding is more and therefore the molecule is unstable. So what is bond order? It is the 1/2 of the difference between the number of electrons which is present in the bonding and the anti-bonding. So 1/2 Nb minus Nb. So if it is a positive bond order means Nb, that is the number of bonding electrons, are more than that of an anti-bonding, and the nature of bond is taken as single, double or triple bonds. So the next is bond length. So what is a bond length? The bond order which is formed between the two atoms, it is taken as an approximate measure. So bond length decreases if the bond order increases. So the next is magnetic nature. So if all the molecular orbitals in a molecule are doubly occupied, the substance is diamagnetic. So if one or more molecular orbitals are singly occupied, it is paramagnetic. So example, O2 molecule. So bonding in homonuclear diatomic molecules. So in hydrogen molecule, it is formed by combination of two hydrogen atoms. One is sigma, one is 2. So the bond order is 2 minus 0 as there are no anti-bonding orbitals. So this is how the MOT diagram is written for the hydrogen atom. Hydrogen atom, two hydrogen atoms. Here the molecular bonding takes place, that is sigma 1s hydrogen molecule. This is sigma star 1s the hydrogen molecule. So in case of helium molecule also it is 1s2. So as it is one helium consists of 2 electrons, so 2 helium consists of 4 electrons. So 4 electrons are occupied as sigma 1s2 and sigma star 1s2. Here the bond order is for anti-bonding and bonding it is 0. So a He2 molecule is therefore unstable as the bond order is 0. It do not exist. So in case of beryllium molecule also it do not exist as bond order is 0. Lithium molecule, the electronic configuration of lithium is 1s2, 2s1. So there are 6 electrons in lithium. The electronic configuration of lithium molecule is sigma 1s2, sigma star 1s2 and sigma 2s2. And the above electronic configuration is written as Kk, that is Kk is the shell structure. So which is occupying the first shell, that is K shell. So it is sigma 2s2. Bond order is half, the number of bonding electrons are 4 minus the 2 electrons, which is the anti-bonding orbitals, which results in 1. So lithium molecule is stable and it has no unpaired electrons and it is diamagnetic. So if it is diamagnetic, lithium molecules exist in vapor phase. So this is how we write the molecular orbital diagram of lithium. So Li 1s 1s, 2s 2s, that is bonding, anti-bonding. Anti-bonding, here it is sigma 2s, sigma star, pi 2px, pi 2py, sigma 2pz, sigma star 2px, sigma star 2py and sigma star 2pz. So this is 1s, 2s, 2p. So one lithium, this is arranged, and another lithium, this is the electrons are arranged. So the next is carbon molecule. The electronic configuration is given below. So the bond order is 2 and the carbon should be diamagnetic. So carbon double bond in carbon consists of both pi bonds because of the 4 electrons which is present in 2 pi molecular orbitals, and a double bond is made up of a sigma bond and a pi bond. So this is in case of oxygen molecule. And 1s, 2s, 2p, 2 electrons, sigma 1s, sigma star. In the same way, the electrons are occupied. So hydrogen bond. So this is the when highly electronegative atoms like nitrogen, oxygen, chlorine are attached to hydrogen atom, it forms the covalent bond, and the electrons of the covalent bond which are shifted towards the more electronegative atom, and this partially positively charged hydrogen atom forms a bond with the other more electronegative atom. This is known as the hydrogen bond. So one is the electronegative atom which forms with the hydrogen. So HF, and these hydrogen bonds acts as a bridge between the two atoms which holds one atom by covalent bond and the other by the hydrogen bond. And the hydrogen bond is represented by a dotted line while a solid line is represented by a covalent bond. So the hydrogen bond is defined as the attractive force which binds the hydrogen atom of one molecule with the electronegative atom of another molecule. So then what is the cause for the formation of hydrogen? So when hydrogen is bonded to a strongly electronegative element, the electron pair which is formed is shared between the two atoms moves away from the hydrogen atom. So as a result, the hydrogen atom becomes more electropositive with respect to the other electronegative atom. So as a result, there is a displacement of electron towards the electronegative atom or the halogen. The hydrogen, it acquires a positive charge, whereas the halogen occurs a negative charge, a fractional negative charge. This is represented by the polar molecule which is having electrostatic force of attraction represented by H sigma, that is delta plus, delta minus, or with fractional positive charge. And the magnitude of hydrogen bonding, it depends upon the physical state of the compound. It is maximum in the solid state and minimum in the gaseous state. So the hydrogen bonds have strong influence on the structure and properties of the compounds. So types of hydrogen bonds. There are two types of hydrogen bonds. First one is intermolecular hydrogen bond and intramolecular hydrogen. In intermolecular hydrogen bond, it is formed between two different molecules of same or different compounds. For example, hydrogen bond in case of HF molecule, alcohol or water molecules. Intramolecular hydrogen bond, it is formed when hydrogen atom is between two highly electronegative atoms which is present within the same molecule. So example, in orthonitrophenol, the hydrogen is present between the two oxygen atoms. So thank you for watching. If you have any doubts, feel free to comment us below. Thank you from AskPrep.